What do you get when you combine a metal nose, a private island, and the most precise astronomical measurements ever recorded without a telescope? The strange world of Tycho Brahe, where science smelled like brass and determination looked like obsession. He worked before the telescope at a royal-funded observatory on the island of Hven. Tonight we're exploring the man who proved the heavens weren't perfect, built instruments so massive they required their own buildings, and whose death remains one of history's most debated medical mysteries. From dueling scars to revolutionary star catalogues, we're uncovering how Tycho's eccentricities weren't just personality quirks. They were the foundation of modern astronomy. But first, we need to understand how a young nobleman's pride would literally reshape his face. You're 20 years old, drunk on wine and academic pride, when someone insults your mathematical abilities. The words hit harder than they should because you know you're brilliant, and everyone else should know it too. But here's the problem with being a Danish noble at a German university in the middle of the 16th century. Honor matters more than sense, and mathematics is apparently worth dying for. Picture Rostock University in December 1566. The stone halls echo with Latin debates and the scrape of wooden chairs. Two young men from Denmark, both convinced they understand numbers better than anyone else in the room, have been arguing for hours about who deserves more respect for their computational skills. You can smell the wine on their breath mixing with the smoke from oil lamps, creating that particular scent of academic arrogance that universities perfect across centuries. The argument starts with equations and ends with accusations. Words like fraud and pretender get thrown around like daggers before actual daggers make their appearance. Because when you're young and drunk and certain you're the smartest person in the room, the logical next step is apparently to grab swords and settle mathematical disputes with steel. So Tycho Brahe and Manderup Parsberg step outside into the winter darkness to duel over who was the superior mathematician. In the courtyard lit by torches, with vision impaired by wine and shadows, steel finds flesh. The blade catches Tycho across the bridge of his nose, slicing through cartilage and bone with a wet sound of metal meeting tissue. The immediate aftermath is chaos. Blood streams down Tycho's face, soaking his shirt and pooling at his feet. The metallic smell mixes with the winter air while Parsberg stands there, probably sobering up fast as he realizes what he's done. Tycho touches his face and feels the devastating truth. His nose is partially gone, carved away by a moment of drunken stupidity. But here's where the story gets interesting, because Tycho doesn't retreat into shame or hide his disfigurement. Instead, he treats this disaster like an engineering problem that needs solving. Renaissance technology wasn't just about clocks and printing presses. It was about rebuilding human bodies when violence tore them apart. The prosthetic nose that emerges from this catastrophe is a masterpiece of practical engineering. Not just a simple metal attachment, but a carefully crafted piece designed to fit perfectly over the damaged tissue. For centuries, portraits showed what appeared to be a silver or gold nose, leading historians to assume Tycho wore precious metals. But 2012 analysis of his exhumed remains confirmed the everyday prosthesis was brass, while gold or silver versions may have been reserved for special occasions. He attaches it with a special adhesive that has to be reapplied regularly, creating a daily ritual that reminds him of his youthful folly. The scent of metal and adhesive becomes part of his personal atmosphere, mixing with whatever he's drinking. Often beer, because Danish nobles consume beer like water, and astronomy apparently pairs well with alcohol. But what should have been a mark of shame becomes something entirely different. The metal nose makes Tycho instantly recognizable in any crowd. While other scholars blend into academic anonymity, Tycho stands out like a walking advertisement for the intersection of violence and intellect. European courts love spectacle, and a brilliant astronomer with a brass nose is the kind of character that kings remember and fund. The prosthetic becomes his calling card, a conversation starter that opens doors across the continent. People expect the man with the metal nose to be extraordinary, and Tycho delivers. The disfigurement that could have ended his social prospects instead enhances his scientific reputation, because in a world full of boring academics, memorable beats perfect every time. Nobles and scholars alike want to meet the Danish astronomer who literally has brass in his face. The nose becomes part of his brand before branding was a concept, a physical reminder that this particular scientist has survived both violence and reconstruction. It suggests someone willing to take risks, to face consequences, to rebuild himself when life cuts him down. The duel also sparked something else in Tycho, a deeper interest in medicine and alchemy that would later influence his scientific approach. Managing his prosthetic required understanding adhesives, metals, and healing processes. The experience of reconstructing his own face gave him insights into the practical side of natural philosophy that pure theorists never gained. Interestingly, Tycho and Parsberg later reconciled, proving that academic disputes don't have to end friendships permanently, even when they involve facial reconstruction. But this physical reminder of youthful pride would pale next to what Tycho had already witnessed years earlier, when the sky itself had revealed a secret that would reshape his entire understanding of the universe. Picture 14-year-old Tycho watching the sun disappear in broad daylight on August 21, 1560. But unlike everyone else, he's taking notes. While neighbors point at the sky and whisper about divine punishment, this kid is scribbling measurements with the focused intensity of someone who suspects the adults don't know what they're talking about. The eclipse darkness feels different when you're the only person treating it like a science experiment instead of the end times. You have to understand what eclipses meant in the 16th century. Most people saw them as cosmic warnings, messages from God written across the heavens in shadow and fire. But Tycho brings something unusual to this celestial drama, a complete lack of religious terror and an abundance of mathematical curiosity. He's armed with the standard astronomical tables that every educated person uses to predict celestial events. These books represent centuries of accumulated wisdom, passed down from ancient Greek astronomers through Islamic scholars to European universities. They're supposed to tell you exactly when eclipses will happen, how long they'll last, and what path the shadow will take across the Earth. But as Tycho watches the eclipse unfold, something bothers him. The timing is wrong. The astronomical tables said the eclipse should have started earlier, lasted longer, or followed a slightly different path. The discrepancy isn't huge, maybe minutes here or there, but it's enough to make a mathematically minded teenager question everything he's been taught about how the universe works. So he starts measuring. While everyone else experiences the eclipse as a religious or emotional event, Tycho treats it like a laboratory experiment. He times the duration of totality using whatever crude instruments he can manage. He notes the exact moment when the moon's shadow first touches the sun, when totality begins, when it ends, and when the eclipse finishes completely. The methodical approach reveals something troubling. The predictions are consistently wrong, not just by a little bit, but by amounts that suggest fundamental problems with medieval astronomy. It's like following a map that puts major landmarks in the wrong places. You might still reach your destination, but you can't trust the directions for anything important. This single observation opens a crack in young Tycho's worldview. If the astronomical tables are wrong about something as dramatic and predictable as an eclipse, what else might they be wrong about? The positions of planets, the timing of seasons, the basic structure of the cosmic order. All of it becomes suspect when your most reliable references can't accurately predict when the sun will disappear. His frustration grows as he continues studying astronomy and discovers that the eclipse wasn't an isolated problem. Star charts place constellations in positions that don't match what you see in the sky. Planetary tables predict conjunctions and oppositions that happen days earlier or later than expected. The entire medieval astronomical system is like a clock that runs slow, close enough to be useful, but too inaccurate to be trusted. But here's what separates Tycho from other students who notice these problems. Instead of accepting the inaccuracies as inevitable, he starts imagining solutions. Most scholars shrug off small discrepancies as the price of doing astronomy with ancient tools and limited observations. Tycho sees them as evidence that someone needs to start over from scratch. The childhood experience plants the seed of an obsession that will consume his entire adult life. He realizes that astronomy isn't just wrong in small details. It's fundamentally broken at the level of basic observations. You can't build accurate theories on top of inaccurate data, just like you can't construct a solid building on a foundation made of sand and wishful thinking. This revelation shapes his life's mission in ways that won't become clear for years. While other astronomers debate the philosophical implications of different cosmic models, Tycho focuses on something more basic: the desperate need for better measurements. Someone has to go outside night after night, year after year, and actually watch what the planets and stars are doing instead of just copying numbers from old books. The Eclipse transforms a law student into an astronomer, but more importantly, it transforms a passive consumer of knowledge into an active investigator. Instead of accepting what ancient authorities wrote about the heavens, Tycho decides to find out what the heavens actually do when you watch them carefully enough to catch their secrets. This wasn't just academic curiosity. It was the beginning of a scientific revolution that would reshape how humans understand their place in the universe. The teenager taking notes during an eclipse was unconsciously laying the groundwork for modern empirical science, where observation trumps authority and measurements matter more than theories. But to achieve the level of precision his vision demanded, he would need resources unlike anything any astronomer had ever possessed. He would need a patron wealthy enough to fund the impossible, and a location where he could build instruments on a scale that matched his ambitions. Where most noblemen would build a fortress, Tycho built a research compound, part observatory, part laboratory, part publishing house. Frederick II grants him the island of Hven, along with generous royal funding that contemporary observers compared to the expense of a princely showplace. Here's a man obsessed with precision, frustrated with existing tools, and convinced that astronomy needs to be rebuilt from the ground up using better measurements and bigger instruments. The astronomical community thinks he's lost his mind. Colleagues whisper that no single project could justify such massive expense, that astronomy doesn't need this kind of infrastructure, that one man's obsession with precision has spiraled into megalomania. They've spent their careers making do with small instruments and approximate measurements. Why would anyone need an entire island to study the stars? But Tycho sees what they don't: that revolutionary science requires revolutionary methods. You can't achieve unprecedented accuracy using the same old approaches that produced the same old errors. If you want to measure planetary positions precisely enough to reveal new truths about how the universe works, you need instruments so large and stable that they dwarf anything previously attempted. So construction begins on Uraniborg, which translates roughly as Castle of the Heavens. The name suggests something grand and otherworldly, but the reality is far more practical and impressive. This isn't just an observatory with a dome and a telescope. Tycho designs a complete scientific enterprise that brings together every aspect of astronomical research under one massive roof. Picture walking through this complex in its prime. You enter through gates that smell of fresh timber and metal polish, sounds of construction mixing with a scratch of quills on parchment. The main building rises multiple stories, with rooms dedicated to different aspects of the astronomical enterprise. Uraniborg includes its own printing press running constantly, producing star charts and treatises that spread Tycho's work across Europe. The paper mill ensures he never runs out of materials for recording observations and publishing results. You can hear the rhythmic pounding of hammers turning rags into writing surfaces, the splash of water wheels driving the machinery. The smell of wet paper and ink permeates hallways where students hurry between workshops and lecture rooms. Student dormitories house young astronomers from across the continent who come to learn Tycho's methods and contribute to his massive observation program. Over time, Roughly 100 people work at the facility. Students, artisans, and researchers who commit years to the project. They sleep in rooms that smell of wood smoke and candle wax, wake to bells that signal observation sessions, and spend their days learning to operate instruments larger than anything they've seen before. Workshops fill with the sounds of metalworking and precision crafting. Artisans forge brass components for astronomical instruments, carve wooden supports that must remain stable for decades, and polish glass lenses to optical perfection. The collaboration between scholars and craftsmen creates a new model for how science gets done, not as individual contemplation, but as organized, systematic investigation. What Tycho creates represents something unprecedented in human history. Science as a coordinated enterprise, instead of lone scholars working in isolation. He organizes teams of researchers who collaborate on long-term projects requiring sustained effort and shared expertise. The concept seems obvious now, but in the 16th century it's revolutionary. The cost becomes legendary even by royal standards. Frederick II essentially funds the equivalent of a Renaissance space program, pouring resources into a single man's vision of how astronomy should be conducted when money is no object and precision is the only goal. This investment creates ripple effects throughout European intellectual life. Other rulers want their own scientific prestige projects. Scholars adjust their career plans around opportunities to work at facilities like Uraniborg. The intersection of royal patronage and scientific ambition produces a new category of researcher, the professional astronomer working with institutional support rather than personal resources. Uraniborg attracts talent from across the continent because it offers something unavailable anywhere else: the chance to do astronomy at a level of precision and scale that individual scholars can't achieve alone. Students arrive expecting to learn observational techniques and leave understanding how scientific collaboration amplifies individual capability. The complex becomes both Harvard and MIT of its era, combining advanced education with cutting-edge research. Visiting scholars bring news of developments in other fields, while residents export Tycho's methods to institutions across Europe. The scientific revolution doesn't happen in isolation, but through networks of communication and collaboration that Uraniborg helps establish. But as impressive as this surface facility becomes, with its workshops and dormitories and printing presses, Tycho has something even more extraordinary planned. The real breakthrough in precision astronomy requires solving problems that surface construction can't address, challenges that demand a completely different approach to instrument design and environmental control. Tycho solves this by digging straight down into solid rock. While everyone else pointed their instruments at the sky from rooftops, Tycho understood something that his colleagues missed. The biggest enemy of precise measurement isn't distance from the stars, but movement beneath your feet. Picture the criticism he faced when construction began on Uraniborg, the underground complement to his surface observatory. Fellow astronomers questioned his sanity, wondering why anyone would build an observatory that couldn't see the sky directly. The concept violated every assumption about how astronomical observation should work, like designing a ship that sailed underwater or a windmill that operated in caves. But to fix accuracy problems caused by wind and building sway, he mounted instruments on bedrock and built Uraniborg underground. You're trying to measure tiny angular differences between celestial objects, fractions of degrees that separate accurate star positions from useless approximations. Every time wind shakes your building, every vibration from footsteps or settling timbers, every slight movement of your instrument support throws off measurements that took hours to set up properly. So he orders his workers to carve multiple instrument chambers directly into the bedrock beneath his island. The excavation creates a series of connected underground rooms, each designed to house specific types of astronomical instruments. The stone walls smell of damp earth and fresh chisel marks, while the floors are leveled to tolerances that contemporary architecture rarely achieved. This engineering marvel solves problems that surface observatories couldn't address. Wind becomes irrelevant when your instruments sit in chambers carved from solid rock. Temperature variations that cause metal instruments to expand and contract get dampened by the Earth's natural insulation. The constant microvibrations that plague tower-based observatories disappear when your measurement platform connects directly to bedrock. The instruments themselves dwarf anything previously constructed for astronomical use. Massive brass quadrants the size of dining tables stretch across the chambers. Complex arrangements of interlocking metal rings that represent the celestial coordinate system in three-dimensional form. Walking among these instruments feels like navigating a mechanical forest where every surface gleams with careful polishing and every joint moves with the precision of expensive clockwork. Each instrument chamber connects to the surface through carefully designed openings that provide clear views of specific portions of the sky while maintaining the structural stability of the underground facility. The openings are large enough to permit unrestricted observation, but small enough to prevent weather from affecting the delicate mechanisms below ground. This stable platform transforms astronomical measurement from an approximate art into something approaching modern scientific precision. His naked eye measurements reached accuracy approaching 1 arc-minute, far better than predecessors. When your instrument doesn't shake with every breeze or shift with changes in temperature, you can detect positional differences that earlier astronomers never knew existed. The improvement in accuracy isn't incremental, it's revolutionary. Tycho organizes a methodical observation program that takes advantage of this unprecedented stability. Teams of assistants work in shifts, tracking individual planets night after night for years at a time. They record not just where Mars appears on a given evening, but how its position changes from hour to hour, week to week, season to season across multiple orbital cycles. The observations accumulate into datasets that reveal patterns invisible to earlier astronomers working with less precise methods. Subtle variations in planetary motion become detectable when you eliminate the measurement errors that plagued surface-based observations. The difference between what ancient texts predicted and what actually happens in the sky becomes impossible to ignore. This systematic approach produces something unprecedented: astronomical data accurate enough to reveal fundamental problems with existing theories about how planets move through space. When you can measure planetary positions precisely enough to detect small discrepancies between prediction and reality, you discover that the entire theoretical framework needs rebuilding. The Underground Observatory operates like a precision manufacturing facility for astronomical knowledge. Raw observations get processed through careful measurement techniques, checked for errors, and compiled into comprehensive records that document celestial behavior with unprecedented detail. The smell of ink and parchment mixes with the metallic scent of brass instruments in chambers that hum with focused intellectual activity. Years of patient observation yield accuracy levels that wouldn't be surpassed until telescopes revolutionized astronomy decades later. Tycho's position measurements prove so reliable that later astronomers use them as the foundation for developing new theories about planetary motion. The data collected in these underground chambers becomes the empirical basis for transforming astronomy from philosophy into science. But this precision came with an unexpected consequence. When you measure celestial positions accurately enough to trust your instruments over ancient authorities, you start noticing things that don't match what the textbooks say should be there. The unchanging heavens were about to reveal something that would make Tycho famous across Europe and challenge everything scholars thought they knew about the cosmic order. On November 11, 1572, Tycho steps outside on a clear evening and sees something impossible blazing in the constellation Cassiopeia. This isn't the subtle appearance of a comet or the gradual brightening of a known star. This is a completely new light burning brighter than Venus, visible even in daylight, appearing where absolutely nothing existed before. The shock hits him like cold water because, according to everything he's been taught about the universe, what he's looking at simply cannot exist. You have to understand the cosmic order that dominated 16th century thinking. Aristotle had declared the heavens perfect and unchanging over 1,000 years earlier, and his word carried the weight of absolute truth. The celestial sphere beyond the moon was supposed to be made of crystalline perfection, where nothing ever appeared, disappeared, or altered in any way. Stars were eternal fixtures, planets followed predictable paths, and the cosmic machinery hummed along with divine regularity that mortal humans could observe but never see disrupted. But here's this brilliant new star mocking centuries of established wisdom, burning bright enough to cast shadows and challenge the fundamental assumption that the heavens never change. Most people see it as a divine portent, another sign that God is sending messages through celestial drama. Tycho sees it as a puzzle that demands systematic investigation rather than theological interpretation. So he does what he always does when the universe presents him with something unexpected. He starts measuring. While others debate the religious implications of this celestial apparition, Tycho hauls his instruments outside and begins the methodical process of determining exactly where this impossible star sits in space. The measurements require night after night of careful observation, tracking the star's position relative to known landmarks in Cassiopeia. He measures the star's brightness by comparing it to other celestial objects, creating a scale that documents how this newcomer outshines everything else in its neighborhood. The light is steady rather than twinkling, which suggests something fundamentally different from the atmospheric effects that make distant stars flicker. This thing burns with a consistent intensity of something much closer, yet its position among the fixed stars suggests it belongs to the supposedly unchanging celestial realm. The most crucial measurement involves parallax, the apparent shift in position that occurs when you observe an object from different locations. If this new star sits closer than the moon, it should show detectable parallax when viewed from different points on Earth's surface. Tycho enlists observers across Europe to take simultaneous measurements, creating a network of data collection that can reveal the star's distance through triangulation. The results shatter the Aristotelian worldview like a hammer through glass. The star shows no measurable parallax, which means it lies far beyond the moon in the supposedly perfect celestial realm. The lack of parallax proved the star existed beyond the moon, directly contradicting Aristotelian claims about celestial immutability. This isn't some atmospheric phenomenon or nearby object masquerading as a star. This is genuine celestial change happening in the region where change was supposed to be impossible. The implications ripple through European intellectual life like shock waves from an explosion. If new stars can appear in the heavens, then the entire cosmic order needs rebuilding from the ground up. The religious establishment panics because their theology depends on celestial perfection, reflecting divine, unchanging nature. University professors find themselves defending textbooks that suddenly seem as outdated as medieval maps showing dragons at the edges of known territory. Academic debates rage across Europe as scholars struggle to reconcile observation with authority. Some try to explain the new star as an optical illusion or atmospheric effect, desperately preserving Aristotelian perfection against the evidence of their own eyes. Others suggest it's a temporary divine intervention that doesn't invalidate the general principle of celestial unchangeability. The intellectual gymnastics become increasingly elaborate as people try to fit revolutionary evidence into conservative frameworks. But Tycho chooses a different approach. Instead of twisting his observations to fit ancient theories, he publishes his measurements and lets the evidence speak for itself. His 1573 book, De Nova Stella, challenges established authority by presenting data that any competent astronomer can verify. The title itself announces his revolutionary intent. This is genuinely a new star, not some explained-away phenomenon that preserves comfortable old assumptions. The publication strategy proves brilliant because Tycho doesn't just make claims. He provides the measurements that allow other astronomers to check his work. When your data is solid enough to survive scrutiny, you can challenge centuries of accepted wisdom with confidence. The book becomes famous across Europe, not just for its controversial conclusions, but for the rigorous methodology that supports them. This represents a fundamental shift in how knowledge gets validated. Instead of deferring to ancient authorities, Tycho demonstrates that careful observation trumps inherited wisdom when the two contradict each other. The new star becomes a symbol of empirical science emerging from the shadow of classical philosophy, proof that the universe reveals its secrets to patient observers rather than scholarly interpreters. The star that appeared in Cassiopeia proved that the heavens weren't perfect, unchanging, or predictable in the ways that medieval cosmology assumed. Tycho's measurements demolished the concept of celestial perfection by showing that even the most distant regions of space could produce sudden, dramatic changes visible to anyone willing to look carefully. But the universe wasn't finished challenging everything scholars thought they knew about the cosmic order. Something even more disruptive was approaching, and when it arrived, it would attack the very structure that supposedly held the planets in their paths. 5 years later, the Great Comet of 1577 arrives to finish what the supernova started. You can picture Tycho standing in his courtyard, watching this brilliant visitor streak across constellations with a sinking realization that everything he'd been taught about cosmic architecture was about to collapse. This wasn't just another celestial oddity to catalogue and file away. This observation, along with the supernova, made the idea of nested, solid spheres untenable. Medieval astronomers believed the universe operated like an enormous clockwork mechanism. Invisible crystal spheres nested inside each other carried the planets along their ordained paths, each sphere rotating at its own speed to produce the complex motions visible from Earth. These weren't metaphorical spheres. They were supposed to be actual solid barriers that divided cosmic space into distinct regions, as real as the walls of a building and just as impenetrable. But comets presented a devastating problem for this elegant system. If the heavens were filled with solid crystal spheres, how could anything move freely through them? A comet passing through multiple planetary spheres would shatter them like a rock thrown through a series of glass windows. The implications made theologians and astronomers equally uncomfortable because the crystal sphere model wasn't just scientific theory. It was the foundation of Christian cosmology. So Tycho begins his painstaking tracking program, hauling his massive instruments outside night after night to measure exactly where this celestial intruder appears against the background of fixed stars. The work requires the kind of obsessive patience that separates real astronomers from casual sky watchers. You have to record the comet's position at the same time each evening, account for atmospheric effects that distort measurements, and maintain accuracy levels that detect tiny changes in celestial coordinates. The measurements accumulate into a detailed map of the comet's path across multiple constellations. Unlike planets that follow predictable routes along the ecliptic, this comet cuts across the sky at angles that ignore the supposed boundaries between crystal spheres. It's like watching a bird fly through what should be a series of glass walls without breaking anything, except the walls are supposed to be holding the entire universe together. But the real breakthrough comes when Tycho applies his parallax measurement techniques to determine the comet's distance. Just as he had done with a new star in Cassiopeia, he coordinates observations across Europe to triangulate the comet's position in three-dimensional space. Tycho observed the Great Comet of 1577 and used parallax measurements to show it was superlunary, thus undermining the idea of solid celestial spheres. The mathematical proof hits the astronomical establishment like a meteor strike. You can imagine the panic this creates in academic and religious circles. The crystal sphere model isn't just a convenient way to explain planetary motion. It's the cornerstone of a worldview that places Earth at the center of a rationally designed universe. If the spheres don't exist, then the entire cosmic order needs rebuilding from scratch. Professors who have spent their careers teaching crystal sphere astronomy suddenly find their expertise worthless. The Church faces an even more serious crisis because Christian theology depends on the idea that God designed the heavens as a perfect, ordered system that reflects divine nature. Crystal spheres provide the mechanism that makes this cosmic order possible, explaining how planets follow their prescribed paths without chaos or collision. If comets can move freely through the heavens, then the universe looks less like divine clockwork and more like an empty void where objects drift according to unknown forces. Tycho's measurements don't just challenge one aspect of medieval cosmology, they demolish the entire theoretical framework. His data proves that the space between planets is empty rather than filled with solid barriers, that celestial objects can appear and move freely through regions previously thought to be permanently fixed, and that the heavens operate according to principles completely different from accepted wisdom. The implications ripple through European intellectual life as scholars struggle to comprehend what replaces the crystal sphere model. If the heavens aren't divided into distinct regions by solid barriers, how do planets maintain their orbits? What prevents chaos from erupting as celestial objects collide with each other? How does the cosmic machinery operate without the structural support that crystal spheres provided? These questions demand answers that existing theories can't provide. The old system lies in ruins, but no obvious replacement emerges from the rubble. Medieval cosmology had provided a complete, self-consistent explanation for everything from planetary motion to divine providence. Now astronomers face the terrifying prospect of starting over with no guarantee that any new system will prove as elegant or comprehensive as the one they've just destroyed. Tycho realizes that destroying the old cosmic order creates an obligation to build something better. His precise observations have revealed fundamental problems with accepted wisdom, but criticism without alternative solutions leaves astronomy in chaos. The situation demands a new model that could satisfy both mathematical precision and theological comfort, a cosmic architecture that nobody had yet imagined. Tycho solves this dilemma by inventing his own cosmic architecture. When you can't choose between Ptolemy and Copernicus, why not create your own universe? That's exactly what Tycho does when faced with two competing models of the cosmos, neither of which satisfies what his precise observations are telling him about how the heavens actually work. The old Earth-centered system can't explain the data he's collected, but the new sun-centered model creates problems that seem just as serious. Picture Tycho sitting in his study, surrounded by years of meticulous planetary observations that refuse to fit neatly into either existing framework. The Ptolemaic system, with Earth at the center of everything, requires increasingly complex mathematical gymnastics to match what he's actually seeing in the sky. You need dozens of epicycles and adjustments to make the predictions work, and even then the results don't match his measurements with the precision he's achieved. But Copernicus's heliocentric model presents its own set of troubles. If Earth really moves around the Sun at tremendous speed, then the stars should show detectable parallax as our viewing angle changes throughout the year. Tycho has looked for this stellar parallax with instruments more precise than anything Copernicus ever used, and he finds absolutely nothing. The stars appear fixed in their positions, regardless of Earth's supposed motion. This creates a mathematical dilemma that keeps Tycho awake at night. Either the stars lie at distances so vast that parallax becomes undetectable even with his best instruments, or Earth doesn't move at all. The first option requires stellar distances that seem absurdly large, thousands of times farther than anyone has ever imagined. The second option means Copernicus got the fundamental structure of the universe wrong. So Tycho develops what seems like an obvious compromise that splits the difference between the two competing systems. He places Earth firmly at the center of the universe, keeping it motionless to avoid the parallax problem. In Tycho's model, the Sun and Moon orbit a fixed Earth, while the other planets orbit the Sun. This hybrid system combines the best features of both models while avoiding their most serious weaknesses. The mathematical elegance of this arrangement becomes apparent once you work through the orbital mechanics. Venus and Mercury stay close to the Sun because they're orbiting it directly, which explains why these planets never appear far from the Sun in Earth's sky. The outer planets follow more complex paths that result from their solar orbits being carried around Earth's central position, producing the looping motions that earlier astronomers struggled to explain. This hybrid model solves the parallax problem that plagued Copernican astronomy while eliminating the mathematical complexity that made Ptolemaic astronomy increasingly unwieldy. You get simpler calculations than the old system required, but you avoid the physical implications that made the new system seem impossible. It's like finding a middle path between two extremes that captures the advantages of both while avoiding their most serious weaknesses. The Tychonic system gains acceptance across Europe, especially in Catholic regions where religious authorities resist the idea of displacing Earth from its central position in God's creation. Church officials can embrace Tycho's model because it preserves Earth's cosmic importance while incorporating the mathematical improvements that make Copernican astronomy useful for practical calculations. You get better predictions without challenging theological assumptions about humanity's special place in the universe. Universities begin teaching the Tychonic system as a respectable alternative to both classical and revolutionary astronomy. Students appreciate its logical consistency and mathematical tractability. Professors like it because they can adopt improved calculation methods without abandoning centuries of established cosmic hierarchy. The model provides a safe middle ground for scholars who want astronomical accuracy without philosophical revolution. But here's the irony that Tycho never fully realizes. His supposedly different system is mathematically equivalent to the Copernican model he's trying to replace. The Tychonic system was observationally equivalent to the Copernican system for planetary positions, which is why it served as a politically and theologically safer compromise. If you transform the coordinate system by shifting your reference point, the Tychonic and Copernican systems produce identical predictions about planetary positions. They're not competing theories, but different ways of describing the same underlying mathematical relationships. The Tychonic system serves as a bridge between medieval and modern astronomy, allowing the scientific community to absorb new mathematical methods while preserving familiar cosmic architecture. It demonstrates how scientific progress sometimes requires compromise solutions that help communities transition between competing worldviews without abandoning everything they previously believed. Tycho creates a model that satisfies the observational requirements of modern astronomy while respecting the theological constraints of his era. The system works well enough to remain influential for decades, providing a framework that professional astronomers can use for practical calculations while avoiding the cultural disruption that pure Copernicanism would have caused. But the true test of any astronomical system isn't theoretical elegance. It's whether someone can use your data to unlock deeper truths about how the universe actually works. For that, Tycho would need a collaborator brilliant enough to see patterns he had missed, stubborn enough to challenge his authority, and ambitious enough to claim credit for discoveries built on decades of someone else's observations. Johannes Kepler arrived in Prague carrying mathematical ambitions that would clash spectacularly with Tycho's protective instincts. Picture this collision of personalities. On one side, you have the aging master observer with his metal nose and decades of meticulous measurements, jealously guarding the astronomical treasure he's spent his life accumulating. On the other side, there's this young German mathematician who shows up convinced he can unlock cosmic secrets that Tycho's been sitting on without fully understanding their significance. The tension starts immediately because Kepler doesn't just want a job. He wants access to everything. He's heard about Tycho's unprecedented planetary observations and believes these measurements hold the key to understanding how the universe actually works. But Tycho treats his data like a dragon hoarding gold, parceling out small portions while keeping the complete datasets locked away from prying eyes. You have to understand how different these two men approach the same problem. Tycho prioritized measurement and control. Kepler prioritized mathematical interpretation. Tycho is the ultimate empiricist, someone who trusts only what he can measure repeatedly with instruments he's designed and calibrated himself. He's spent decades perfecting observational techniques, training assistants to operate massive brass quadrants, and building underground chambers that eliminate every possible source of measurement error. For him, astronomy means patient accumulation of precise data, night after night, year after year. Kepler operates from the opposite direction. He's a mystical mathematician who believes the universe follows elegant mathematical principles that can be discovered through theoretical insight rather than endless observation. He sees patterns where others see chaos, geometric relationships where others see random planetary wandering. The man literally believes that planetary orbits should follow musical harmonies because God designed the cosmos as a celestial symphony. This fundamental philosophical difference creates constant friction in their working relationship. Tycho wants to collect more data before drawing conclusions, while Kepler thinks they already have enough observations to reveal the underlying mathematical laws. Tycho insists on methodical verification of every measurement, while Kepler pushes for bold theoretical leaps based on limited datasets. The power struggle becomes personal because both men understand what's at stake. These aren't just abstract intellectual disagreements. Whoever controls Tycho's observations will control the future direction of astronomy. The data represents 20 years of systematic planetary tracking with unprecedented accuracy, measurements that won't be duplicated for decades. Access to this information means the difference between revolutionary discoveries and continued theoretical speculation. Their collaboration on the Rudolphine tables reveals the depth of their conflict. This massive project aims to create the most accurate planetary tables ever produced, combining Tycho's observational data with improved mathematical methods. But they constantly argue over methodology, with Tycho demanding conservative approaches that stick close to the measurements, while Kepler pushes for theoretical models that explain the data through underlying physical principles. The fights aren't just about scientific methodology, they're about credit and control. Tycho wants the tables to reflect his life's work as the master observer who made the measurements possible. Kepler sees himself as the mathematical genius who's transforming raw observations into profound insights about cosmic mechanics. Both men have legitimate claims to ownership, but their egos make compromise nearly impossible. You can picture the atmosphere in their shared workspace, thick with tension and mutual suspicion. Tycho locks away his most valuable observations while grudgingly sharing selected datasets that Kepler needs for specific calculations. Kepler works with whatever data he can access while constantly pushing for more complete information. The collaboration produces results, but neither man trusts the other's ultimate intentions. Their conflict reflects the broader transition happening in astronomy during this period. Observational astronomy, represented by Tycho's methodical data collection, is giving way to theoretical astronomy based on mathematical modeling and physical principles. Kepler embodies this new approach, using observations as raw material for discovering universal laws rather than treating measurements as ends in themselves. The irony is that both men need each other more than they're willing to admit. Tycho's observations, without theoretical framework, remain just collections of numbers. Kepler's mathematical insights, without reliable data, become pure speculation. Their partnership, however bitter and contentious, represents exactly the kind of collaboration that scientific revolution requires. Empirical precision combined with theoretical boldness. But the collaboration can't last because their personalities are fundamentally incompatible. Tycho sees Kepler as an impatient theorist who wants to rush toward conclusions without properly understanding the observational foundation. Kepler views Tycho as a data hoarder who's afraid to let his measurements be used for the revolutionary discoveries they make possible. Kepler and Tycho clashed over data access. After Tycho's death, Kepler used Tycho's measurements to derive his laws. Their bitter partnership would ultimately produce the laws of planetary motion and the mathematical foundation of modern celestial mechanics. But Tycho would never witness this triumph, never see how his meticulous observations would be transformed into the theoretical framework that revolutionized astronomy. The political winds that had supported his work for 2 decades were already shifting, and soon Tycho would face challenges that threatened everything he had built. Christian IV's coronation in 1588 brought immediate changes that would destroy everything Tycho had built. After 20 years of royal support, Tycho suddenly found himself unwelcome in his own country. New kings mean new priorities, and the expensive astronomer with his island laboratory doesn't fit into the fresh political landscape that's emerging in Denmark. You have to understand how completely Tycho's life depended on royal favor. Uraniborg wasn't just his observatory, it was his entire world, funded by a king who believed that scientific prestige reflected royal greatness. The annual budget for maintaining this astronomical empire rivaled what most nobles spent on their estates. But Frederick II considered it a worthwhile investment in Denmark's intellectual reputation across Europe. Christian IV's court sees things differently. The new king's advisors view Tycho as an expensive relic from the previous reign, a scientific curiosity whose usefulness doesn't justify his enormous cost. They whisper about the fortunes spent on brass instruments and underground chambers, while pressing domestic needs go unaddressed. The math is simple. Why fund one man's cosmic obsession when the money could build ships, fortify borders, or reduce taxes? The political shift creates an impossible situation for Tycho. He spent 2 decades building the most advanced astronomical facility in history, training assistants, perfecting instruments, and conducting the systematic observations that represent his life's work. Everything he's accomplished depends on continued royal support, but that support evaporates as the new administration distances itself from its predecessor's extravagant scientific patronage. The abandonment becomes painfully obvious through a series of budget cuts and bureaucratic obstacles that make continuing his work increasingly difficult. Funding gets delayed, then reduced, then threatened with complete elimination. Tycho finds himself arguing with royal accountants about instrument maintenance costs and staff salaries, defending expenses that were never questioned under the previous king's generous patronage. Picture the agony of watching your life's work crumble through administrative indifference. Tycho faces the prospect of dismantling Uraniborg piece by piece, selling off instruments he designed and built over decades of careful development. The massive quadrants and armillary spheres that enabled his revolutionary measurements become expensive brass that could be melted down for more practical purposes. The library presents an even more heartbreaking loss. Tycho has accumulated thousands of books, manuscripts, and observational records that represent the intellectual foundation of his scientific enterprise. These aren't just personal possessions, but the accumulated knowledge base that makes advanced astronomical research possible. Leaving them behind means abandoning the scholarly resources that took decades to assemble. By 1597, Tycho finally abandons Ven entirely. He left with some instruments, entrusted others to caretakers, and began his desperate search for new patronage across the courts of Europe. He's 53 years old, too invested in his scientific career to start over in a different field, but too expensive for most rulers to support at the level his work demands. The search becomes humiliating as he essentially begs for the kind of support he once took for granted. Letters go out to every European court that might appreciate the prestige of employing the famous astronomer with the metal nose. Tycho emphasizes his international reputation, the revolutionary discoveries he's made, and the continued potential for scientific breakthroughs that proper support could enable. But most rulers see him as a luxury they can't afford, interesting but not essential to their political or military needs. The breakthrough comes through Holy Roman Emperor Rudolf II, whose court in Prague has become a magnet for scholars, artists, and intellectual curiosities from across Europe. Rudolf appreciates the kind of esoteric learning that other rulers dismiss as impractical, and he understands how scientific patronage enhances imperial prestige. In 1599, the emperor offers Tycho a position that promises to restore the research conditions he's lost. But starting over at age 53 proves more challenging than Tycho anticipated. The move to Prague means rebuilding everything from scratch, finding suitable locations for instruments, training new assistants, establishing the administrative systems that keep a major research program functioning smoothly. The work that took decades to perfect in Denmark must be compressed into whatever years remain in an aging astronomer's career. The construction of a new observatory begins at a castle outside Prague, but the facility never matches the scale or sophistication of Uraniborg. Time pressures and limited resources force compromises that Tycho would never have accepted in his prime. The instruments are smaller, the staff reduced, the systematic observation programs abbreviated compared to what he achieved during his Danish period. The irony becomes apparent as Tycho struggles to recreate his scientific empire, while his health begins showing signs of the wear that decades of obsessive work have inflicted. Just when he needs energy and stamina to rebuild his astronomical program, his body starts failing in ways that suggest his most productive years are behind him rather than ahead of him. Tycho's exile marks the end of the greatest observational program in pre-telescopic history. The systematic measurements that revolutionized astronomy become impossible to continue at their previous scale and precision. The scientific enterprise that bridged medieval and modern approaches to understanding the cosmos fragments as its creator faces the limitations of age and circumstance. But the final chapter of his story would unfold in the most unexpected way possible, at a dinner party where social etiquette would collide with biological necessity in a manner that baffled physicians for centuries. Tycho's final banquet becomes the opening scene of a medical mystery that will puzzle investigators for 4 centuries. Picture this scene from aristocratic etiquette hell. You're at a formal dinner hosted by nobility, surrounded by the kind of people whose opinion matters for your career, and nature calls with increasing urgency. But leaving the table before your host dismisses the gathering would be a social catastrophe that could destroy your reputation forever. Kepler, who witnessed the evening, later described how the dinner dragged on for hours with a ritualized pace that 16th century nobility perfected as a form of social torture. Course after course arrives while Tycho sits there, probably shifting uncomfortably in his chair, feeling the mounting pressure in his bladder, but unable to do anything about it without committing an unforgivable breach of protocol. The choice becomes stark. Humiliate yourself socially or endure physical discomfort that's becoming genuinely painful. Tycho chooses etiquette over biology, a decision that transforms a normal bodily function into the opening act of what seems like a straightforward medical case. He sits through the entire banquet, maintaining the composed demeanor expected of a distinguished scholar, while his body screams for relief that social convention won't permit. But modern forensic analysis reveals that murder is now considered unlikely, based on 2010 and 2012 exhumation results that found no evidence of acute poisoning or foul play. The real story proves far more complex than simple bladder retention. Contemporary accounts describe severe urinary problems that begin almost immediately after Tycho finally escapes the dinner table. Something has gone seriously wrong with his urinary system, creating pain levels that suggest actual tissue damage rather than simple irritation from holding his pee too long. For 11 days, Tycho writhes in agony that defies every medical treatment available to Renaissance physicians. A physician at the time suggested kidney stones, because what else could cause such severe urinary problems in an era before modern diagnostic techniques? The explanation seemed obvious and fit the available evidence perfectly, but later autopsy found no stones, leaving the immediate cause of death unexplained and opening the door to centuries of speculation. Delirium sets in as the mysterious illness progresses, turning the brilliant astronomer into a babbling patient who drifts between consciousness and fever dreams. His final words reflect the obsessions that dominated his entire career. He keeps muttering about not living in vain, as if he's reviewing his scientific accomplishments while his body shuts down around him. The mystery deepens over the centuries as historians and medical experts propose increasingly elaborate theories. Mercury poisoning becomes popular because Tycho spent years conducting alchemical experiments that exposed him to toxic heavy metals. Murder plots capture the imagination of writers who see dramatic potential in court intrigue and scholarly rivalry. with various suspects proposed as villains who supposedly eliminated the inconvenient astronomer. 20th and 21st century analyses found mercury traces consistent with long-term alchemical exposure, but not acute, lethal poisoning levels that could explain his rapid death. The evidence suggests occupational exposure from decades of experimental work rather than deliberate assassination, but still doesn't account for the specific urinary symptoms that killed him. Modern paleopathology suggests urinary failure was likely a complication of conditions such as prostatic hypertrophy, urinary retention, or metabolic disease, the kinds of medical problems that wealthy, sedentary men in their 50s commonly develop, especially when their lifestyle includes rich food and limited physical activity. The symptoms match what you'd expect from urological complications, rather than exotic poisoning or dramatic murder plots. Each generation of medical experts brings new techniques and perspectives to the mystery, but the fundamental questions remain stubbornly unanswered through historical analysis alone. Did etiquette really contribute to killing one of history's greatest astronomers? Or was something more complex at work? The evidence points in multiple directions, while definitive proof remains elusive based on written accounts and indirect analysis. The death that seems straightforward, a man dies after holding his pee too long, becomes one of history's most analyzed medical cases. Libraries fill with papers proposing new theories, testing old hypotheses, and debating the evidence with the intensity usually reserved for major historical controversies. Tycho's final illness generates more scholarly attention than most people's entire careers. The truth about what killed the famous astronomer with a metal nose would require more than theoretical analysis and speculation based on centuries-old accounts. The answers lay buried with Tycho himself, waiting for modern science to examine the physical evidence that historical records couldn't provide. In 2010, scientists opened Tycho's tomb and discovered that the real killer wasn't poison, politics, or even his bladder. The exhumation represented the kind of forensic detective work that modern science makes possible, bringing 21st century analytical techniques to bear on a 400-year-old mystery that had spawned countless theories but no definitive answers. Picture the anticipation as researchers prepared to examine Tycho's remains using methods that would have seemed like magic to Renaissance physicians. Would they find evidence of mercury poisoning that supported the assassination theories? Traces of kidney stones that confirmed the medical explanations? Or something completely unexpected that had eluded centuries of speculation? The scientific analysis began with comprehensive toxicology testing that could distinguish between different types of mercury exposure and identify their likely sources. Multi-element hair and bone analyses found mercury residues consistent with long-term exposure from alchemical activities, and separate analyses found traces of gold exposure in hair. These indicate occupational exposure rather than an acute poisoning event. Unlike the crude hair analysis from earlier decades, modern techniques can determine whether toxic metals accumulated over years of experimental work rather than arriving all at once through poisoned wine or murderous rivalry. The mercury results proved anticlimactic for conspiracy theorists. The exposure was chronic rather than acute, building up gradually through years of experimental work rather than arriving all at once through deliberate assassination. But the real breakthrough came through bone pathology studies that revealed conditions invisible to historical accounts. Modern forensic analysis can read human skeletons like medical textbooks, identifying diseases that affected their owners' daily lives without necessarily causing dramatic symptoms that contemporary observers would notice or record. The bones told a story that had nothing to do with dramatic poisoning or royal intrigue. Tycho's skeleton shows diffuse idiopathic skeletal hyperostosis, DISH, and markers of obesity and a high animal protein diet, which increase the plausibility of metabolic comorbidities such as possible diabetes and benign prostatic hyperplasia that can cause urinary retention and renal failure. DISH typically develops in people who combine genetic predisposition with lifestyle factors that 16th century nobility perfected into an art form. Rich diets loaded with meat and alcohol, sedentary work that involves sitting for hours at desks or observation platforms, and the kind of metabolic stress that comes from decades of intellectual obsession and irregular sleep patterns. Picture Tycho's daily routine during his prime years at Uraniborg. He spends nights hunched over massive brass instruments, making precise measurements that require maintaining awkward positions for extended periods. Days get consumed by mathematical calculations performed while sitting at tables covered with charts and computational aids. Meals feature the kind of rich fare that wealthy Europeans consider appropriate for distinguished scholars. The combination proves deadly over decades. Tycho's skeleton shows the unmistakable signs of someone whose elite lifestyle gradually destroyed his body's ability to function normally. The precise observations that made him famous required physical positions and work patterns that systematically damaged his spine, joints, and internal organs. Dietary isotope studies added another piece to the puzzle by revealing what Tycho actually ate during his final years. The analysis shows a diet heavily weighted toward meat and alcohol, with limited plant matter and the kind of nutritional profile that modern medicine associates with metabolic syndrome and organ failure. The irony hits like a punch to the stomach. The man who revolutionized precision measurement was killed by the most mundane causes imaginable: obesity, poor diet, and the accumulated physical stress of decades spent pursuing scientific perfection. No dramatic poison, no political conspiracy, no romantic tragedy, just the slow grind of rich food and sedentary work, destroying a brilliant mind housed in an increasingly dysfunctional body. The bladder problems that dominated his final days now make perfect sense in this context. DISH affects the entire skeletal system, including the bones and joints that support the organs responsible for waste elimination. Add in metabolic dysfunction from decades of poor dietary choices, and you get exactly the kind of urinary complications that killed Tycho after that fatal dinner party. The etiquette explanation becomes a tragic footnote rather than a primary cause. Holding his pee at the banquet probably triggered the final crisis, but the underlying conditions that made such a crisis possible had been developing for years through lifestyle choices that seemed perfectly reasonable for a wealthy intellectual. Modern forensic science reveals Tycho as a victim of success rather than intrigue. The royal patronage that funded his astronomical empire also provided the rich food and sedentary lifestyle that slowly destroyed his health. The focused intellectual work that produced revolutionary observations also created the physical stress patterns that damaged his skeleton and internal organs. The mercury traces that fueled centuries of poisoning theories turn out to represent exactly what they appear to be: evidence of extensive alchemical experimentation rather than sinister assassination plots. Tycho died not as a victim of courtly intrigue, but as a victim of the diseases of affluence that wealthy intellectuals have suffered throughout history. But the forensic analysis of Tycho's remains was only the beginning. When archaeologists turned their attention to the ruins of his abandoned laboratory, they would discover evidence of experimental work that challenged everything historians thought they knew about Renaissance science. Archaeological analysis of glass and ceramic fragments from Uraniborg revealed traces of tungsten, surprising because tungsten isolation is usually dated much later, and this result invites careful interpretation and further study rather than immediate conclusions. Picture the moment when modern analytical equipment identifies this element in ceramic fragments and glassware recovered from the ruins. The scientists probably stared at their readouts for several minutes, checking and rechecking results that made no sense according to the official timeline of chemical discovery. Tungsten wasn't supposed to be isolated and identified until the late 18th century, when Swedish chemists finally managed to extract this incredibly dense metal from its mineral ores using techniques that required advanced furnaces and chemical processes. But here's physical evidence that suggests Renaissance experimental chemistry may have been more advanced and deserves cautious re-evaluation. The discovery emerged from painstaking archaeological analysis of Uraniborg's underground chambers, where Tycho conducted the alchemical experiments that represented the hidden side of his scientific career. While everyone knows about his astronomical achievements, Fewer people realize that he spent just as much time and energy pursuing the ancient art of transmuting base metals into gold and creating medicinal compounds from mineral ingredients. The laboratory remains tell a story of sophisticated experimental work that pushes the boundaries of what we thought Renaissance scientists could accomplish. Glass fragments show evidence of high-temperature processes that required furnace designs more advanced than standard historical accounts suggest were available. Ceramic crucibles contain residues from metallurgical experiments that involved purifying and combining materials in ways that demanded precise temperature control and chemical knowledge. The lab residues also contained gold, mercury, and lead, consistent with serious alchemical operations. The mercury traces help explain the elevated levels found in Tycho's remains, but they also illuminate the scope of his experimental program. This wasn't casual dabbling in mystical practices, but serious laboratory work that involved heating, distilling, and combining toxic materials in enclosed spaces where vapors could accumulate to dangerous levels over years of regular exposure. Gold residues suggest experiments aimed at understanding how precious metals could be created artificially, the ultimate goal that drove centuries of alchemical research. The presence of partially purified gold indicates that Tycho wasn't just studying existing materials, but actively trying to transform cheaper substances into more valuable ones using techniques that combined practical metallurgy with theoretical chemistry. Lead appears in forms that suggest it was being used as raw material for transmutation experiments, probably following traditional alchemical recipes that claimed base metals could be elevated to noble status through proper treatment with the right combination of heat, chemicals, and timing. The laboratory becomes a place where scientific observation meets practical experimentation in ways that blur the line between rational investigation and mystical pursuit. The discovery illuminates how Renaissance scientists like Tycho operated across multiple fields that modern education treats as completely separate disciplines. His reputation rests on astronomical achievements, but the laboratory evidence shows someone equally committed to medicine and metallurgy, pursuing knowledge through hands-on experimentation rather than just theoretical study. These underground chambers weren't just places where Tycho conducted secret experiments. They were research facilities where he explored the connections between celestial observation and terrestrial chemistry. Alchemists believed that planetary influences affected chemical processes, so someone mapping the heavens with unprecedented precision would naturally want to understand how cosmic forces influenced the transformation of matter. The broader revelation suggests that Renaissance science was far more experimental and advanced than standard historical accounts acknowledge. While textbooks focus on the theoretical breakthroughs that challenged medieval worldviews, the archaeological evidence reveals practical experimental work that pushed technological boundaries in ways that wouldn't be formally recognized until much later periods. Tycho's true legacy lies not just in the stars he mapped with revolutionary precision, but in the unknown experiments he conducted in darkness beneath his famous observatory. The combination of astronomical observation and alchemical experimentation represents a holistic approach to natural philosophy that treated the universe as an integrated system where celestial and terrestrial phenomena followed related principles. The tungsten mystery forces us to confront uncomfortable questions about how much Renaissance scientists actually accomplished versus how much they chose to document for public consumption. Secret laboratory work might have achieved breakthroughs that remained hidden because political and religious authorities viewed such experiments as dangerous or heretical. The man with the metal nose spent his life proving that precision and obsession could unlock secrets that casual observation missed entirely. His story reveals how the strangest personalities often produce the most revolutionary discoveries, and how true scientific progress requires the kind of methodical dedication that most people would consider completely insane. From astronomical precision to alchemical mysteries, Tycho's life reveals how scientific revolution emerges from the most unlikely combinations of obsession and circumstance. His metal nose became the calling card for measurements that shattered crystal spheres and revealed tungsten centuries early. The underground chambers, where he mapped planetary motion with unprecedented accuracy, also hid alchemical experiments that pushed Renaissance chemistry beyond official timelines. His legacy lives on every time we point a telescope at the sky, measure with instruments, or trust data over dogma. His refusal to break court etiquette likely triggered an acute urinary crisis, but modern forensic and paleopathological evidence points to long-term occupational and lifestyle factors, including chronic metal exposure from alchemy, obesity, and dish metabolic syndrome that made such a crisis fatal. If this made you curious, like and subscribe, only if you actually enjoy the ride. Let me know in the comments where you're tuning in from and what time it is for you.